Local search is another technique of approximation. It also aims at solving the hard problems approximately. What makes it different is that it concentrates at local optimum. Let's take a look at one example to see how it works. So here we have a bowl where the global minimum is sitting at the bottom. And our task is to find this global minimum. So what we do first is to make an initial guess at somewhere else, and then search in a neighborhood. But first we define a neighborhood around this point, and then search in this small neighborhood a best direction to go. All right, and when we realize that this is the direction that can help us go deeper, then we move along this direction for one step. Okay, and again, we just repeat this. Every time we just search in a small neighborhood, that is to search locally, and move step by step and getting closer and closer to the global minimum. So it's like a while loop, right? So when can we jump out of this while loop? It's when no improvement is possible. So it looks simple, right? What makes it complicated is a situation like this. Do you see my point? In case that there are many local minimums on the way, we can easily get trapped into any one of them, right? So it depends on two things. One is the initial guess. If we can make a very good initial guess, hopefully we can eventually stop at the right position, the global minimum. However, if we are somewhere else, for example, somewhere here, it's going to be very much likely to get trapped into this local minimum, right? And the second key is the step size. Even if we don't have a very good initial guess at the very beginning, if our step size is large enough, still it's possible for us to jump out of this, right? But it's hard to say. Say for example, if we take a good initial guess here, but the step size is too large, we might say jump from this position to the next position. And then in the worst case, we're going to be bouncing back and forth forever, right? So here comes the next question. Can this algorithm actually terminate in a finite number of steps? So these are the difficulties we have to face when we do local search. There are two keywords in local search. They are local and search. Local means we define neighborhoods in the feasible set. A local optimum is a best solution in the neighborhood. So that's what local means. Okay? To do search, we start with a feasible solution as the initial guess and search a better one within the neighborhood. A local optimum is achieved if no improvement is possible. And there are some notations about neighbor relation. And we write something like S tilde S prime, means that S prime is a neighboring solution of S, means that S prime can be obtained by a small modification of S. So we just change S a little bit to obtain S prime. All right, so that's this notation. And next is N of S, stands for neighborhood of S, which is the set of all those S primes that can be obtained by small modifications of S. All right, and the technique we used in the previous example is called gradient descent. So we start from any feasible initial guess, and we initialize the mean cost to be the cost of that solution, and then get into this while loop. All right, every time we search in the neighborhood of this S and try to find the best S prime, okay, and calculate its cost. If this cost is better than the mean cost, then we update the mean cost and update the solution. So move forward until what? Until this is no longer true. It means that for the best S prime in this neighborhood, we cannot make this mean cost any better. Then we can break and return S. And the name gradient descent means that first of all, we are descending, getting down. Secondly, we are descending along the direction that will help us to make the deepest move. And that direction is the gradient of the point. If you still remember what gradient is, 梯度, alright? In calculus, 我们在微积分里学过的. So that's why it has this name. Next, we're going to apply local search to 3 famous NP-hard problems.